Yeah. So the topic of this meeting is unitarity and beyond, and I must admit I will go far beyond. And it is remarkable that by listening to talks, there are a lot of mentioning of Efimov state, but the only proven stable state is of helium trimer. Everything else they qualify as resonances, but in other words, they are unstable. Now, what happens if we start growing and adding more and more helium atoms? And in theory, again, you will have tiers and tiers and tiers of Efimov states, but it's not what we observe. And as the first speaker already noticed, we are coming to quantum clusters, and that is what my talk will be about. Now, if we look at helium, helium has two isotopes, helium-4, which is bosonic, and helium-3, which is fermionic. They both qualify as quantum liquids. In that they stay liquid to absolute zero. And you can compare with common mundane argon. Now, all other substances besides helium, they have this point. This is a triple point where solid, liquid, and gas coexist. But in quantum liquid, there is no such a point. So they are liquid down to absolute zero temperature. And helium-4 goes superfluid below about 2.2 Kelvin. Whereas helium-3 also goes superfluid, but at much lower temperature. So for the purpose of this talk, helium-4 droplets will be superfluid, and helium-3 droplets will be non-superfluid. So why we are interested in droplets, and what is the scope of our range? Well, first of all, we are interested in isolated superfluids. Before, in low temperature physics, superfluids were of course studied quite a lot, but they're always in contact with duar or surface or something, which often limits the range of applicability. So we can produce droplets. Our droplets may be very large or very small. So let's say starting from 1 nanometer containing a few hundreds of atoms to 1,000 nanometer, which will contain 10 to the 9, 10 to the 12 helium atoms. Now, in vacuum, that's all in a molecular beam. In vacuum, the helium-4 droplets will have a temperature of about 0.4 Kelvin by evaporative cooling, and helium-3 about 0.15 Kelvin. And well, we cannot change temperature much because it is set by evaporative cooling and the length of our molecular beam apparatus. But important is now for us is to compare phenomena we observed in helium-4 and helium-3. Now, a lot of interest in different communities actually are related to the fact that we can put something inside. We can put a molecule, like a regular molecule, an atom, or charge, for example, and then this charge will be isolated in a quantum fluid, so we can study, for example, spectroscopy. Now, rotation is another interesting phenomenon. The particles inside can rotate, and we can study rotational spectra and learn an interaction between molecule and quantum fluid, or the entire droplet can rotate. And that will be more in focus of my talk today. Now, actually, most of the groups in this field are in field of physical chemistry, I would say, and because it turns out the droplets are exceptional metrics to do spectroscopy of molecules and ions. Now, some groups do femtosecond dynamics of molecules, and they found very long coherence time upon oxidation, mass spectroscopy, reactivity at low temperature, and formation and deposition of metal clusters are another activities. Now, my talk would mainly be concentrated on rotation in quantum liquid droplets. There will be larger droplets of the order of submicron, and in superfluidity in finite droplets. Other projects, which I will probably not talk today, they involve quantum phase transitions, like, for example, helium-3, helium-4 phase separation in droplets. We can also do experiment very fast, so one can study superfluids far from equilibrium. We recently also started studying charged droplets, and well, there are also experiments on ionizing droplets completely and obtaining solid-state density plasma. And it turns out that helium is a very promising case here. And we do it with X-ray imaging. Now, before coming to superfluidity, I'll just give you a couple of examples how the infrared spectra look like. So, for example, we can take an ion, C2H3+. Well, that's a real ion. It is very important in astrochemistry, actually, and it is in all kind of schemes for production of larger ions. And here's a comparison. So this one is a traditional way of doing spectroscopy, also in molecular beams. So they attach argon atom to it, and they do this so-called tagging spectroscopy. Usually the temperature here is not very low. It's about 100 Kelvin. So you get this contour, a lot of other features. Now in helium, you have very narrow feature, and clearly it's much better. We can resolve much more lines. We can expand it to larger ions of significance to chemistry. Another example from my work back in Germany is we discovered that molecules, like especially simple molecules like oxygen, carbon, sulfur, this is a linear molecule, they rotate in helium-4 droplets. So this is a rotational vibrational spectrum. So vibrational frequency is here, and those are delta J plus -1 transitions. Now from here we can get a moment of inertia, which turns out to be different from the gas phase. From the intensity distribution we can get a temperature, which is 0.38 Kelvin, and those were relatively small droplets, about 6,000 helium atoms. Now, we knew that at this temperature droplets should be superfluid, so we thought, well, this free rotation is a manifestation of superfluidity, and but we couldn't change temperature much because it is set by evaporation cooling. So we went to helium-3 isotope, and we do experiment with the same molecule, and you can see the spectrum gets much broader. And if you feed the lines, the distance between lines is much smaller. So we get an interpretation that this is a microscopic manifestation of superfluidity, and our molecular probe feels the superfluid or non-superfluid state. However, this molecular probe is a local probe. It interacts with liquid helium on a van der Waals distance, like, well, let's say sub-nanometer. And superfluid is known to be characterized by a macroscopic wave function, and which is characteristic of the entire droplet. And so if we have, let's say, cylindrical symmetry or spherical symmetry, we may write a macroscopic wave function in such a way, the generic way, and we can obtain velocity as a gradient of phase. And it turns out that velocity will have a singularity in the center and go as 1 over r, which is a quantum vortex state. Now, another important property is if we have a curl of velocity, will be 0 everywhere, except if you make a contour around the center, where this velocity circulation will be integer number of kappa, where the kappa is a quantum circulation. So that is a quantum vortex. So the circulation is quantized. And well, essentially, like I see Feynman first noticed that this curl of velocity can be expressed as kappa times delta function, where this Rj is the position of a vortex. Now, if vortices rotate in the same direction, they repel each other, and they form a type of a Wigner crystal. So it was predicted that vortices will form a triangular lattice. Well, if you look at rigid body rotation and take curl of a rigidly body rotating in any point, the value will be 2 times omega. And it turns out that in superfluid, it's on average. If you have an average value of this curl, that will be 2 times of omega. But the average value of a curl is kappa quantum of circulation type times areal number density of vortices. So there is a relation between number density of vortices and angular velocity, and we will use it later. Now we're going to, I'm experimentalist, and how we produce our droplets, and essentially we do a very similar experiment as Reinhardt already told us, we expand helium through a small orifice. Now, his experiments are done at relatively low pressure, stagnation pressure in this area, and high temperature or higher temperature. But we go to higher pressures and lower temperatures. So essentially, at a very low temperature, we expand the liquid itself. And then liquid, for example, here, it's an optical microscopy. Liquid jet breaks into droplets. And well, each droplet in this particular case is of the order of 5 micron. And then our experiment is somewhere later on. We believe when liquid helium comes through the nozzle, the liquid acquires vorticity. So in this case, it's still a normal fluid, but once it goes into vacuum, the vorticity gets captured by droplets, and droplets cool rapidly within hundreds of microseconds, maybe faster, to below superfluid transition, and we must have quantum vortices. Now, I will show you later that it is actually difficult to observe quantum vortices in helium because they're so small. And for that, we dope droplets with xenon atoms and or with other atoms, and we believe that atoms should be attracted to vortices by hydrodynamic forces, and that gives us a contrast for observation. Now, one of the motivation of our initial motivation was to see how superfluid droplets rotate, and in particular, the shapes of rotating classical bodies like rigid body rotation was studied at great detail, starting from Newton. Each great mathematician in the 19th century contributed to part of it, and it turns out that well, spherical droplet, once it gets rotating, it gets into spheroidal or pseudo-spheroidal shape. And then at some point, there is a bifurcation into elongated shapes. And well, here there are 3 axial ellipsoidal or quasi-ellipsoidal. And then at some point, they get this pill shape or even dumbbell. And at some angular momentum, they are no longer stable, and they break apart. And this liquid drop model plays a large role. It turns out that the planets, they follow this, but droplets, they follow a similar diagram, and they can be described by the same sequence of shapes. Well, they will also apply for rotating nuclei. So now we ask ourselves, what would be the rotation in quantum droplet? And rigid body rotation is characterized by velocity which rises linear from the center. But we already know that in vortex, it goes as 1 over r. There is another motion in a droplet which can carry angular momentum, which is, let's say, quadrupolar capillary wave. And this is a velocity field in such a wave. It's still very different. Now, in quantum droplets, we may only have vortex or quadrupolar capillary wave where rigid body rotation would correspond to hugely excited state, I mean, huge energy. So we wonder if you have only this and this, how it will map into rotation. Now here we have a difficulty. Now I copied a picture from Eric's former work, and they observed vortices in BEC optically, but you can see the diameter of vortex is of the order of 10 micrometers, so you can see it optically, whereas our entire droplet is 1 micrometer diameter, and the diameter of a vortex is about 0.2 nanometers. So first of all, we cannot even observe such droplets optically at reasonable resolution. So, and second, vortices are even more difficult. So we need to go to X-rays, essentially, and as many people in this room, we came to accelerators, but like different types. So we used free electron lasers, and in essence, the relativistic electrons in accelerator, they then come through this periodic magnetic structure, and they somehow produce coherent X-ray beam. And this is well, if you drive about 200 miles north from here, you will cross the structure, which is a free electron laser at a SLAC at Stanford, and we did experiments here with some experiments. And the experiment is very simple. We have our droplets nozzle. We expand helium and vacuum. It breaks into rotating droplets. We add, in some experiments, we add xenon to mark vortices. And then we do, we cross it with X-ray beam, and we observe diffraction. And we process diffraction, and then we learn from diffraction, whatever we can learn. Now, why this experiment work is because of the huge intensity of the free electron laser. We worked at 1.5 kiloelectron volts, 0.8 nanometers. So the laser produces 10 to the 12 quanta per pulse, and the pulse is 100 femtoseconds. So for any purposes, our droplets are moving, of course, but they are moving much, much slower than 100 femtoseconds. The beam is focused to about 25 square micron. It runs at 120 hertz at the time of our experiment. So you can calculate from a refractive index, if you put a droplet of 1 micrometer diameter precisely in a focus, we will produce 10 to the 8 scattered photons. So it's a large number. Each photon at 1.5 kilo electron volt can be detected. There will be also about 10 to the 6 photon absorbs, which means ionization. So we can do experiment only once on each droplet. So once the droplet is ionized, it breaks apart. Now, as you notice, there is a continuous nozzle and pulsed like X-ray laser. So most of the laser shots will be empty, I mean, dark images, but we will have 1 to 10 per minute bright shots, which we then somehow select and analyze. And well, eventually only the most intense are analyzed, as I will show later. So that's our experiment. It's actually a user experiment. We only supplied nozzle, so droplets fly here, X-rays go here, and then somewhere they cross. And we have this array detector. It's all provided by the facility, so we just come and bring our source. That was a product of large collaboration. We have several beam times starting from 2012, and here we did several beam times at LCLS, at SLAC. We also did a couple of beam times at European Free Electron Laser in Hamburg. And from collaboration, especially I'm grateful to Oliver Gessner and Christoph Bostad. And Oliver is LBNL, and Christoph was a beam scientist and LCLS. And they introduced me to this, and since then we collaborate. Well, our last beam time was online during COVID. It was a tough beam time. So we were all here, and then only a few people could do experiments upon our directions. And it was very difficult, actually. I don't want to repeat. But, well, we were lucky, and from the very first experiments, we observed nice signals. And for example, here's a diffraction from a neat droplet. And you can see like IRI type pattern. And this is elastic scattering. The intensity here is given by some analytic equation in terms of Bessel function 3/2. So because we know all parameters, we can get radius and the number of atoms in a droplet. And again, this is just one shot. There is no averaging. This was this particular droplet, and it's just, or each image is just unique. Now, well, this is other droplet. You can see the distance between rings is much smaller, so it's larger droplet, and we can, let's say, measure the sizes. We also observed that some contours are circular, but other contours are elliptical, or we even have this strange contours with streaks, and we assign them to spherical, spheroidal, or elongated droplets. And in each case, we can get half axis, but as I'll show on the next slide, we can, well, our images corresponds to diffraction from a density profile. So in a sense, well, we are not sensitive to like 3D. We only see 2D projection, and sometimes it's limitation. Sometimes we can go around it, but that's the little bit of scattering theory. We are here in Rayleigh Ganz approximation, which means that we are optically seen at 1.5 kilo electron volts. Again, this intensity is actually 3D Fourier transform, but it can be reduced to 2D Fourier transform. So this is now the density profile. And well, we measure, of course, modulus squared. So we don't record this phase information, which then requires some more work to get density out of diffraction. Now, just to mention, there is another collaboration in Europe around Daniela Rupp, Frank Stinkemeyer, and others, and they did experiments at other X-ray laser in Trieste, and this is XUV laser, so much longer wavelengths, actually much larger cross-section for X-ray scattering, and they can see 3D images because now this is a large angle scattering, and you can see that they can fit the shapes to this particular diffraction images. So this is very nice. It has a promise. Unfortunately, this is no longer optically seen, and the reconstruction of density get much more complex, and it is actually not achieved yet. So here, for example, we also compare. We can determine size distribution of the droplet and aspect ratio distribution of the droplet, and for like helium-4 droplets are usually small. Helium-4 droplets are usually larger, but they usually can be described by exponential distribution. So this log of count, and the same aspect ratio can be described by approximately exponential distribution. That means that in our beam, at our conditions, we have a large distribution of sizes and shapes, so angular momenta. This is good and bad, but it's good because we can span large range, which we just wait. We turn on our experiments, wait for several hours, and we have a large set of data. Now, as I said, in order to see vortices, we added xenon, and once we add xenon, the images get very different. So we still have rings, but we also have a lot of speckles, and those speckles are interference of X-rays between, well, scattered from xenon clusters, but also scattered from the droplet. And sometimes you can just do pen on paper. For example, this image corresponds to 2 clusters of xenon, like approximately equidistant, which is like 2-slit experiment. They produce this periodic structure stripes, and droplet produce rings, and then interference, constructive interference gives you bright spots, and destructive gives you no spots. So it can be done, but in general, for example, image like this cannot be easily interpreted, and we adapted a phase retrieval algorithm, which was first done by FineUp. And the idea is that our intensity is the sum of amplitude squared, and one is from droplet, which we know analytically, and the other one is from clusters, which we have to determine. And somehow we can do iterative algorithm and determine the density of xenon clusters. And so you can see this one we now reconstructed without any approximation. Now this one gives 6 dots, and we believe those are 6 vortices imaged approximately along the axis. And here we have 6 filaments, which we believe they mark the vortices. And we have quite a number of those images. And in helium-4, we always get filaments. But we wanted to check with helium-3, which is normal fluid in our conditions, and indeed we get very different images. So there are no vortices in helium-3. Now xenon rotates in a droplet frame and centrifugate to the outside. So in a sense, we get rings in a helium-3. Mm-hmm. So now, well, those are 3 representative images. Now, if you have a spherical droplet, then, well, this droplet contains 15 vortices, and they are imaged at some distance. But we can get density of the vortices. Now this is ellipsoidal droplet. Now here the vortices are in the middle, and now this one is a pill-shaped droplet. And then here we have an array, like periodic structure, which also evidenced by Bragg spots in a diffraction. Now, from analysis of it, we can obtain angular momentum and angular velocity. And the particular interesting case is in this elongated droplet. Now, here we can use Feynman relation and just get angular velocity from this formula using number density of vortices, and we will get angular velocity. And now we can compare the shape of the droplet, quantum and classical. And actually, what is interesting is that the shapes within our accuracy are the same, although of course mechanism of rotation is very different. In classical droplet, we will have rigid body rotation, and in quantum, it is approximately even contribution from capillary waves and from vortices. Let me skip. So, like in conclusion, so we have, of course, in spherical droplets are quiescent. There is no angular momentum. Now, in axially symmetric droplets, the angular momentum comes from array of vortices, and they have axially symmetric shape, quasi-spheroidal. Now, if you have non-axially symmetric droplets, then the angular momentum is contributed by capillary waves and vortices. And the larger the aspect ratio, the larger the amount of capillary wave contributes. So we can, well, we hope that in the future we can reconstruct this diagram for rotation and a shape for quantum droplets. Let me skip some slides. Yeah, sorry, something happens, but it was at the very end. Well, anyway, I want to thank my collaborators and to thank the generations of my students who run this project and did all those dim times. And thank you for attention.
For this nice talk. So we have time for questions.
So I was wondering, if you have just empty vortices, wouldn't you also see them in your diffraction pattern? Why do you have to fill them up with xenon atoms? And I was also thinking, I know from other experiments where atoms are more typically sitting on the surface of the helium atoms, helium droplets. So how is that working for xenon?
Yeah, well, first of all, well, in principle, it's correct. You will have some modulation from empty, but let's say if a droplet is if the droplet is 1 micron and the vortex diameter is 0.2 nanometers, then the modulation will be of the order of 10 to the minus 3 squared, 10 to the minus 6. So if you measure 10 to the 12 photons per diffraction, you will see it. But otherwise, it will be statistically like not significant. So you will not see any modulation. And that actually, yeah, you can see that like this is one of the brightest image, and you don't see any modulation. And eventually, we realized at the beginning of the experiments, we thought maybe there is one vortex. But eventually we realized that in all droplets of this size, there are many vortices, and the amount of vortices is given by average vorticity we produce from the nozzle. So there must be vortices here too, but there is no modulation. Now another question on outside, inside, and well, from the known species, alkalis are known to be on the outside, like lithium, potassium, sodium, rubidium. I think they were studied by a group of scholars a long time ago, but then Frank Stinkemeyer and Wolfgang Ernst in Graz. But those are the exceptions. All closed shell atoms and all molecules we know, they stay inside and they have reasonable binding energy of the order of a few hundred Kelvin. So they are all inside. So xenon would have a binding energy of the order of, I forgot, 150 Kelvin.
But the xenon likes to be also where there's a modulation in the superfluid density somehow.
This is, yeah. Well, let's say, let me try. I don't know what is going on. Well, anyway, if you have a vortex, then because the velocity is singular in the middle, so the amount of kinetic energy per volume of a liquid is maximum close to the center. Of course, in the center itself, there will be a hole, but it's very small. That means that if there is a vortex and we replace part of the liquid by atom, we are gaining energy because I mean we displaced the moving liquid. Now, and that means that if you go close to the center, this gain of energy will be larger. It's not very large. There were calculations for xenon, and you gain 5 Kelvin if you like go inside vortex or outside. But 5 Kelvin is a lot if you have 0.4 Kelvin temperature. Also, once you start producing cluster, this gain of energy scales with volume. Well, it's approximately, but if you get larger and larger entity, it gains larger and larger binding energy to vortex. So for that reason, well, it is known that if you have vortex in the river, so people can be drowned, and that's the same effect in a sense.
You assigned some angular momentum to the vortices. I missed how you get the angular momentum. You measured density.
Well,
right?
let's say if you have a rectilinear vortex in the middle, then the amount of angular momentum will be h bar times number of atoms in your system. So in our case, well, if you have 10 to the 9 atoms, one vortex, so we will have 10 to the 9 h bar. Now, if, let's say, if you have a 2D system, like I have shown you, then, of course, vortices will not contribute the same, but it can be shown that it will be 1/2. So you have number of vortices times number of atoms times h bar divided by 2. And a similar formula can be derived for a sphere. For the case of rectilinear vortices, I think it will be 2/5 instead of 1/2 coefficient. Frankly, of course, our vortices are not rectilinear, so this is our estimate. But currently, there is no real calculations of non-rectilinear vortices of arbitrary shape in a droplet.
Go ahead.
Well, I have another question. Do the vortices couple in any way to molecules which you put in?
Couple, you mean in a sense of
Exchange angular momentum?
or angular? Well, back when I did a lot of rotational spectroscopy, there were ideas, and I had idea. Let's say if you have a linear molecule and you have a vortex, and then the linear molecule will like to align along the vortex for the reason of this excluded energy. And well, we tried linear molecules like tetracene, pentacene, but we never observed any effect. So the answer is there must be an effect. We never observed it because probably in small droplets there are no vortices. But in large droplets, this experiment is much more difficult because, well, the single molecule in very large droplets is difficult to observe.
Thanks for the nice talk. So maybe a very naive question. The number of helium atoms in your droplets was rather high. So how many do you need in order to have at least one vortex in the droplet? Is there a minimum number, and does it coincide with when the droplet becomes superfluid?
Well, there are different definitions of superfluidity. I maybe Dörde calculated with Brigitte Woolley a long time ago, maybe Brigitte before you. But for example, well, I mean, the definition of all superfluidity is superconductivity based on non-classical response. So when your system responds non-classically, for example, in superfluid, if you will move particle at less than 50 meters per second, this Landau critical velocity, theory tells there will be no drag. But in order to have this, you need this Rotan minimum. So people said that one of the criteria is when this Rotan minimum comes. We know that if a droplet has few thousands of atoms, there is already Rotan minimum from our spectra. A theory says that Rotan minimum start appearing at around 60. So very small number. With vortices, again, theory can calculate vortices in, like, say, 100 atoms. And they believe that those vortices are stable. But if you have a vortex in this kind of system, it will be huge angular velocity. So most likely in our experiments, we just cannot produce this huge angular velocity. Our vorticity corresponds to omega of the order of 10 to the 7. And that means that distance between vortices at this vorticity is about 100 nanometers. So our idea is that if you produce droplet much less than 100 nanometer diameter, there will be no vortices. And it seems to be correct. We did other experiments in Europe at smaller droplet sizes, and it seems they don't have vortices.
Yes. You can observe the formation of the droplet to divide, to fission in two droplets, or they are always stable and remains a droplet? Could divide it in two? Or?
They can, yeah. I mean, first of all, the droplets are very stable. Nothing to do with this elusive states. I mean, the binding energy of one atom to the droplet is 8 Kelvin. The droplet has very reasonable surface tension. So when droplet will set into a highly rotating state, at some point it will split in two. But again, this can be predicted for like a particular droplet size. I think.
Hi.
Is it answer or no? I just want to go to that picture, but I mean, your question was whether it can split, right?
Yes.
Yeah, I mean, it can split if it has a large amount of excitation. And the excitation can be either vibration, like capillary wave, or rotation. And we actually, it's here, like, why is that slide? Something is crazy in that slide. So when you go to larger and larger angular momentum for a given droplet size, like here. So this is reduced angular momentum. Somehow all droplets can be, of all sizes, can be mapped on reduced angular momentum. So in this point, with reduced angular momentum 2, the system is no longer stable. And so you see it goes into this, like initially you have elongated triaxial ellipsoid, then you have pill shape, but eventually you have dumbbell and a very like small place in between, and then it will go away. Those events are rather rare, so we do see such droplets, but we cannot really like make enough images to see the event. But this event is well known in classical droplets, like water droplet. You can spin them with electric field, for example, and they will break apart.
Thank you.
Yes, thank you for the nice talk. I was wondering about one thing, if you could have, if you could see vortices without having a rotation, let's say having vortices that have two different signs. And in particular, if I understood correctly, you are crossing the superfluid transition after producing the droplets. And could you see something that are like Kibble-Zurich vortices?
Mm-hmm. Well, I mean, there was this Kibble-Zurich theory, and the theory tells that, a theory tells that if you proceed over superfluid transition very fast, then you will have spontaneous formation of superfluid with different phase in different places, which is equivalent to vorticity. And then you will like form tangle of vortices or something. We never observed that. However, the experiment is, I would say, in early stage. For example, we are working very far away from the source. So we are at maybe 5 milliseconds away. But experiment can be done very close, like here. And you can observe different things. Like what I say, superfluidity far from equilibrium. So usually what people observe, they cool very slow and they observe thermodynamics mostly. In our case, we can probably observe kinetics because in this range here, let's say the surface will be superfluid because it cools, but the inner will be normal fluid. And you may observe a lot of like interesting effects. But again, this is a beam time experiment. We need to go by steps.
Yeah, okay. Thank you very much.
Is a curiosity, naive question. When you put angular momentum in your helium droplet, in the ground state, this angular momentum prefers to be distributed in vortices. Yes. So you have like excited and less excited states.
You mean, well, I mean, you can still have the entire, more or less through h bar continuous number of angular momenta, because you can produce. So you let's say you have your droplet. You can produce rectilinear vortex, and as I said, it will be n h bar. Angular momentum will be, but you can produce like this type of arc-shaped vortex, and well, the arc can be smaller and smaller, and then you can get less and less angular momentum up to 1 h bar. If you now beyond this, you may have several vortices, and then in a sense, you can produce any angular momentum with the discreteness of h bar, but because it's very large h bar, 10 to the 9 or whatever, you will not see it. And so it's quasi-continuous way. Oh, they will rotate. Let's say we now, this is a side view. Now we look on the top, let's say. Well, we have vortices, and omega will be n vortices, this copper half. So that means that the vortices will be stationary in a rotating frame, but in a droplet frame, well, in a laboratory frame, the entire picture will rotate with omega.
Great. Thank you very much.
Sure. Thank you.
Beautiful talk.